Hi. In this lecture, we're going to talk about a really simple model of aggregation. So here's the thing I want to model. I want to model a situation where you've got a group of people. It could be 100, could be 1,000, and each one is independently going to make a decision to do something. Could be to, go to the gym, could be to go to the beach, could be to go to the grocery store. What I want to try and understand is if you've got a whole bunch of people, each one's making these independent decisions, what's the number of people that shows up? Now, to characterize that, I'm going to use an idea called a probability distribution. So to make this simple, let's suppose that there's a small group of people, like my family, which has 4 people in it. And I want to know what's the distribution of number of 4 people who go for a walk on a given Saturday. Well, if I think about it, the numbers could be, there could be 0 people that go, there could be 1, there could be 2, there could be 3, or it could be that all 4 of us decide to go for the walk, right? The dog would prefer if all 4 of us went, but there's going to be some number that goes. So I could keep track of data. I could chart this on like my wall somewhere. I don't, but you could, right? And you could ask, what's the likelihood that nobody went for a walk? And maybe that's 10%. Now, what's the likelihood that one person went for a walk? Well, that might be 15%. And what about 2 people? That might be 40%. And what about 3 people? That might also be 15%. And then what's the likelihood that 4 of us went for a walk? That might be, let's say, 20%. Now, the thing to note about a probability distribution is each one of these probabilities is less than 1, right? And if we sum them up, we get 25 plus 40 is 65, plus 15 is 80, plus 20 is 100. So we get a total of 100%. So what a probability distribution tells us is what are the different things that could happen? 0, 1, 2, 3, and 4. And then it tells us the likelihood of each of those things. Okay, so here's sort of the huge result that we're going to leverage to understand how things add up. There's a theorem called the central limit theorem. And what the central limit theorem tells us is that if I add up a whole bunch of individual independent events, so what does independent mean? It means my decision to go to the beach is independent of your decision to go to the beach, which is independent of your cousin Mary's decision to go to the beach. So by independent, I mean not influenced. So I don't care whether you're going to the beach or not. I'm going to make my decision on my own. It's completely independent of what you decide to do or your cousin Mary. So what the central limit theorem tells us is if a whole bunch of people make a whole bunch of those independent decisions, the distribution that we get has this nice bell-shaped curve. And this bell-shaped curve means that the most likely outcome is the one right in the middle. So there's a lot of structure to what happens, and that means we can predict a lot of things, and we can tell a lot about what's going on in the world. And that's what we'll learn in this lecture. So it's going to be a lot of fun. To get an understanding of where these distributions come from, let's start really simple. So suppose I flip a coin twice, and I want to know what are the odds of getting a head? What's the probability distribution over heads? Well, what could I get? I could get tails, tails, now it'd be 0 heads. I could get tails, heads, or head, tails, and both of these would be 1 head, or I could get head, head, and that would be 2 heads. So what's the probability of each of these? The probability of getting tails, tails is just a fourth. The probability of getting 1 head is a half, and the probability of getting 2 heads is a fourth. So I'm going to get a probability distribution. If I do it out like this, 0, 1, 2, there's a 1/4 chance of that, a 1/2 chance of that, and a 1/4 chance of that. You notice it sort of looks like a little bell curve. Okay, let's suppose I flip it 4 times. Well, this gets harder. Like I think, okay, what are the odds of getting no heads? I could get tails, 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 tails. Well, how do I figure out the probability of that? Well, it's 1/2 times 1/2 times 1/2 times 1/2. 4 1/2, so that's 2 times 2 times 2 times 2. So that's 1/16. What are the odds of getting 1 head? Well, I could get the head first, and then 3 tails. I could get it second. I could get it third. And it could come last. So there's 4 places it could show up. So that means there's a 4/16 chance. Well, I could do all sorts of math again. I figure out what are the odds of getting 2 heads, and I'd actually get 6/16. And 3 heads, well, that's the same as getting 1 head, really, right? Because tails and heads are interchangeable. So what I get is I get this again. If I do this distribution out, I'd get a peak at 2 heads, right? I'm going to get a nice bell curve, right? So I'm going to get this nice thing where there's very little chance of getting no heads, not that much chance of getting 4 heads, but the most likely thing is getting 2 heads. So I can count all this stuff and it's fine. But here's the problem. Remember, we talked earlier in this class about big data. There's lots of data out there. We want to try and understand it. Well, oftentimes we're going to have more than 2 or 4. We're going to have n. We have some huge number. So if we're talking about New York City, that could be 10 million people. If we're talking about Ann Arbor, where I live, That's still like 100,000 people. So I don't want to be sitting there writing tails, 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 tails 100,000 times. I want to have a model that will help me explain it. So what you can do is you can think, okay, first off, if there's n things, the mean, the expected number should be n over 2, right? It should be half of n. But what we'd like to do is understand sort of what that distribution looks like. Well, what we know from statistics is that distribution is actually going to be a nice bell curve. And the mean, right in the middle of this thing, is going to be n over 2. And then it's going to sort of flow out nice and symmetrically from each side. Now, there's a fancy equation, a formula, right, that tells you what this line looks like. We're not going to get into that, but if you take a statistics class, which I'd encourage you to do because it's a lot of fun, you can learn exactly what this formula is and how it works. Okay? We just want to use it. There was a model for understanding how things aggregate, so we're going to sort of take some leaps ahead in statistics. Here's the trick, though. We got to be a little bit careful. Flipping a coin, it's always equally likely, right? It's either a head or a tails. Each one's 50-50. But if I'm worried about people going to the beach, right, or people going to the supermarket, or people showing up for their flight, that's not a 50-50 proposition, right? So maybe 90% of people may show up for their flight, but maybe only 10% of people or 15% of people go out to the beach. So I'd like to change that 1/2 to something else. Well, I can introduce something called the binomial distribution, where instead of having 1/2, there's just some probability p of doing the thing. So let's suppose going to the beach happens 15% of the time. Well then, if I have 1,000 people, and p equals 15%, then p times n is 150. So I'd expect to have 150 people show up. So that makes sense, but then I can ask, well, what's the distribution though, right? I mean, 150 is the average, but I could have 200, I could have 74. Well, again, what the central limit theorem tells us is that we're again going to get a nice bell curve, right? So we got this nice shape here, but now with a mean here of just p times n. Now this holds provided n is big enough, right? But if I get a pretty large n, you're going to get this nice bell curve, and the mean's going to be right at p times n. Okay, there's more though. Here's where it gets a little bit complicated, but also interesting. There's something called the standard deviation, and this is this thing called sigma, which is this called the standard deviation. Now, when I draw a normal curve, there's going to be a mean, that's this point right here at the center, and then there's going to be a standard deviation, which basically tells us how far spread out that curve is. And what I mean by that is how far spread out the different outcomes are. So it'll turn out there's this nice structure to any normal distribution, that if you tell me the mean, and then you tell me the standard deviation, it's always going to be the case that 68% of all outcomes will be between -1 and +1 standard deviation. So if it's got a big standard deviation, that means that that range could be really wide. And if it's got a small standard deviation, that means that range will be really tight. But if you tell me the mean and tell me the standard deviation, it's always going to be the case that 68% of the time I'm between -1 and +1 standard deviation. Now, in fact, since that's 2 for 1, it's also going to be 2 for 2 and 2 for 3 and 2 for 4, right? So there's going to be a 95% chance I'm within 2 standard deviations. So wait, why do we care about this? Why do we care about this at all? Here's why. Now I've got this model that says if I add up a bunch of independent events, here's what the mean is, right? Now, in a second, I'm going to show you formula for the standard deviation. So I'm going to tell you what sigma is here. Well, if you know the mean and you know sigma, then I can give you a range and I can tell you, that 95% of the time I'm going to be between -2 sigma and +2 sigma. So if I said the mean number of people that show up is 100, and that's the mean, right, and the standard deviation is only 2, well, then you know 95% of the time you're going to be between 96 and 104. So you'd know, okay, I should prepare for pretty much exactly 100 people. If I told you the standard deviation was 15, then you'd know it could be anywhere between 70 to 130. So that's what we want to try and use this model to explain, like sort of how wide a range of outcomes we're likely to see in any particular setting. So let's go back to our simple binomial distribution where the probability was 1/2. The mean, remember, is just n over 2. Well, you can do a little bit of math and show that the standard deviation is the square root of n over 2. So let's suppose I have n equals 100. So if n equals 100, that tells me the mean is going to be 50. So if I flip a coin 100 times, guess what? The average is 50. No surprise. But standard deviation is the square root of n over 2. So what's the square root of 100? That's 10. So this is 10 over 2. So that's just 5. So what that tells me is, if I think of my normal distribution, right, if I draw this thing out, I've got a mean of 50, and then I've got a standard deviation of 5. So that means between 55 and 45, 68% of all outcomes. So if you want, you can do this at home. It'll take a while. Flip a coin 100 times. Count how many heads you get. Flip it again. Count how many heads you get. Do that a whole bunch of times. You'll find that 68% of the time you get between 45 heads and 55 heads. So what this model gives us is it gives us a sense of how strange of outcomes we'll get. So we know that most of the time, 68% of the time, will be between 45 and 55. Right? So our mean was 50. One standard deviation was 55 and 45. That means two standard deviations is 60 and 40. So what that tells us is 95% of the time, you're going to be between 40 and 60 heads. And 99% of the time, you're going to be between 35 and 65. So it basically means you're almost never going to throw fewer than 35 heads and never throw more than 65 heads. And so this is what sort of the power of that central limit theorem is, right? It gives us a sense of not only the average, but also what the spread will be. Okay, but remember, this is a simple case, right? This is the p equals 1/2 case. And what we'd like is we want it for the more general case where the probability of something happening can be anything, right? This is this p over n thing. Well, it turns out here we're okay because the standard deviation is just p times 1 minus p times n, the square root of the whole thing. So in the case where p equals 1/2, right, then we just have the square root of 1/2 times 1/2 times n. But notice I've got a 1/2 squared here inside, so I can just pull that outside. So it's just 1/2 the square root of n. So that's where that square root of n over 2 came from. So now, for the binomial distribution, I've got this clean formula as well, and we can use that to model and understand stuff that's a little bit more interesting than just flipping a coin. Okay, let's do a real example. Let's have some fun. So, most of us have probably been bumped off a plane before, right? So you show up at the airport and there's like, too many people showed up for the plane. And you think, why do they do this? Well, the reason that they sometimes have to bump is they oversell. And the reason they oversell tickets is because not everybody shows up. So if you're running an airline and you've got 400 seats, and people only show up, 90% of the time, you want to sell more than those 400 seats, right? So that your plane's pretty much full. So let's do an example. Let's suppose, to make it simple, that our plane doesn't have 400, it's got 380 seats. So let's suppose that we got a Boeing 747 with 380 seats. Let's suppose that 90% of the time people show up. So we've gathered, we run an airline, we've gathered lots of data. We pretty much know 90% of the time people show up, and that it's independent. So one person's decision to show up doesn't have anything to do with anybody else's. Now that might be true, right? Because if it's snowy, if I'm late, you're likely to be late. But let's just suppose that these things are independent. And let's suppose that we sell 400 tickets. Now we want to try to get some understanding, like, okay, what does that mean? What's the likelihood if we sell 400 that we're going to have more than 380 people show up? Here's where the model can help us, because it'll tell us what the mean is. It'll also tell us what the standard deviation is. So the mean, right, if I sell 400 tickets and on average 90% of people show up, that means I should sell on average 360 tickets. That's less than 380 seats, so I should be fine. But what I care about, right, is more than 380 people show up. So more than 380 show up, guess what? They're going to be mad, right? Because they're going to be like, I paid for this trip to go to Florida. I want to go to Florida. I don't want to be bumped. So the 360 doesn't tell us enough. We want to know something about the distribution. Okay, well, look, we've got a formula, right? Remember, so n was 400 and p was 0.9. So p times n is 360. That's our mean. Now, the standard deviation we can solve for pretty easily. That's just the square root of p, which is 0.9, times 1 minus p, which is 1, times n, which is 400. So if we multiply that out, that's 0.9 times 0.1 times 400. 0.1 times 400 is 40, times 0.9 is 36. So that's just the square root of 36, which is 6. So 6 is our standard deviation. So now I know I've got a bell curve with a mean of 360 and a standard deviation of 6. Okay? Well, that's useful. That can help us, because let's go back and let's look. That means our mean's 360. Our standard deviation is 6, so that means 68% of the time we're going to be between 354 and 366. That's great. It means that 95% of the time we'll be between 348 and 372. Also great. It means 99.75% of the time will be between 378 and 342. Well, how many seats did we have? We had 380 seats. So this means that 99.75, actually more than that, right? More than 99.75% of the time, we won't overbook. So here's the central limit theorem. So let's say it formally. Central limit theorem basically says the following. I've got a whole bunch of random variables. So those could be decisions to show up to a flight or not. So in those cases, the random variables are just ones or zeros. Or they could be, the weight of your bags. Each person's weight of their bags is some independent variable. As long as those things are independent, so that means that each person's decision doesn't depend on somebody else's, or how much stuff I jam in my bag doesn't affect how much you jam in your bag, and that those things have finite variance. What does that mean? That means that they're bounded. So, we can't have super huge values. Like, so my bag couldn't weigh billions and billions of pounds. As long as there's sort of, the possible range of values that each one can take is bounded in some way, or doesn't, with some high probability, take huge values. Then when you add those things up, when you sum them up, you're going to get a normal distribution, right, which means a bell curve, which means we can predict stuff, right? We can use that model to make sense of how the world works. Now, let's step back for just a second and think about, why this is so cool. Suppose it weren't true, right? Here's a little thought experiment. Suppose it were the case that when I added up a whole bunch of independent events, most of the time I got something nice, right? But then there was some spiky probability of some huge event over here. What would this mean? Well, this would mean like sometimes you'd go to the grocery store and there'd be like 1,000 people there. Or sometimes you'd be like, I'm just going to run to the bathroom and there'd be 300 people in line, right? A lot of the predictability of the world, a lot of the predictability of just sort of daily comings and goings stems from the fact that this can't happen and that we get these nice bell curves. Because if individual people, individual firms, individual groups of people make decisions that don't depend on what other people decide, if they're sort of independent decisions, then what you're going to get is you're going to get sort of nice, regular stuff according to a bell curve. Yeah, sure, there'll be traffic jams. Sure, there'll be a lot of people at the mall. Yeah, there'll be days when you get a lot going on. And yes, there'll be days when not much is going on. But most of the time, you're going to get things in that middle region, which is going to be predictable and understandable. Now, is everything normally distributed? No, it's not. So what about stock returns? So if you look at stock returns, you'll actually see that there's far too many days where really nothing happens, and there's far too many days where there's huge gains, and far too many days where there's huge losses. And what's going on there is that the actions are no longer independent. So for example, if prices are going up, a lot of people may buy, and that's going to cause prices to go up even further. And if prices start to fall, people may sell, and that can cause prices to fall even further. So when events fail to become independent, or fail to satisfy the independence assumption, then we can get more big events than we'd expect and more small events than we'd expect. So let's put a bow on this. What have we got? So we've used the central limit theorem as a model. We've used it as a model to explain how if we add up a whole bunch of independent events, then what we get is we get a nice normal distribution, right? And we can understand the mean, we can understand the standard deviation, and we can use that to predict how likely things are to occur, right? We also learned that it's that independence that gives us that normality, right? Without independence, we could get really big events, really small events, we can get all sorts of strange stuff happening. So where we're going to go next, there's a brief lecture on something called Six Sigma that pushes this idea of sort of the predictability of a system a little bit further than we had before. But then after that, we're going to start, we're going to really take the gloves off. We're going to start having systems where there's interdependent actions. When we have those interdependent actions, we're no longer going to get these sort of nice bell curves. We're going to get all sorts of really interesting, strange stuff. It's going to be a lot of fun. All right. Thank you.